Okay, so let's do the last part of this chapter in which we are going to finally arrive at the complete set of Maxwell's equations. Okay, calling it as fixing Ampere's law in electrodynamics and hence getting Maxwell's equations. 8C1. Uh, what was the electromagnetic laws before Maxwell? Okay. Let's look at that one by one. Now we are of course, there is the empirical law of depending on the force on electric field and magnetic field. There's a Lorentz force, uh, and the Coulomb's law, del E. Okay, and then we had del cross E, which was zero in electrostatics, but now in Faraday's law, electrodynamics, we have picked up this changing magnetic field. So that was already Faraday's contribution. Of course, we know we have not been able to find any magnetic monopoles so far. So that is divergence of B is zero. And then, of course, curl of B in magnetostatics, the source of B seems to be the steady state current. So this were the laws. Of course, it was not stated in this form before Maxwell, but the basic physical content was really this. So this is, of course, Gauss's law. Some people call this law as the no magnetic monopole, or sometimes people call it Gauss's law for magnetism. Okay, we just say it is no magnetic monopole. And then this is Faraday's law. We have discussed it now for quite some time. And then this is, of course, Ampere's law. Okay, so this was the status of differential form of the equations, which sort of described all the experiments and electromagnetic phenomena. Of course, in addition to that, there was the uh, continuity equation. Okay, this is not an independent equation. Please check that whether it's an independent equation that you will require, or you can derive it from somewhere. Okay, so but as far as these four laws in terms of divergence and curl, this was the status. So Faraday's law, of course, okay, there is if I take the Faraday's law and take a divergence of this curl, okay, then divergence of this curl is divergence of minus del B by del T. And if I now use the no magnetic monopole, okay, minus del B, then this is equal to 0, and hence this is 0. Now, notice that on the left hand side, I have a mathematical 0. And hence, if these equations are consistent, then it should indeed happen, and it does happen. For Faraday's law, the divergence of the curl is 0. Now let's take the Ampere's law and do the same thing. This is also a curl. So divergence of curl, mu naught divergence of J. And for steady state, of course, it is divergence of J is 0. So that's fine. Okay. But what if we can have non-steady currents? So obviously, on the left-hand side, I have a mathematical identity. On the right-hand side, there's a physical condition being, when it will be true. It should always be true. Okay, so there is a problem there. So this is 0 only if divergence of J is equal to 0, which is magnetostatic conditions. So what happens to non-steady currents? Okay, and so this has to be 0 because this is mathematically, as I said, divergence of a curl must be 0. But for non-steady current, we know continuity equation, divergence of J should be minus del rho by del T. Now that is on the left side I have a 0, and if it is non-steady, this is non-zero, minus del rho by del T. And that is indeed a fatal inconsistency in Ampere's law. Of course, Ampere's law was not meant to be used for non-steady conditions. But what if? Okay, there are phenomena. Okay, and so J can be non-steady, and that's only a restraining condition. but this is not any restraining condition. So hence, there seems to be a problem with this Ampere's law. Okay, so let's look at another view. This is the mathematical view of the inconsistency. Let's look at the physical view, especially it is normally described with charging of a capacitor. And charging of a capacitor, as you know, is not a steady current. Okay, it's a current which keeps changing with time. Okay. So in that case, so consider the process of charging a capacitor. So this is a capacitor, okay, and I can, so there is a current flowing from the battery, okay, which is charging it. Now I can choose an Amperian loop, okay. Of course, for this Amperian loop, I know how much current is going in okay. So Ampere's law would read then, okay, that is divergence of B dot dA is B dot dL, and that is mu naught INC. This should always be true. All right. So let us apply it to Amperian loop and Amperian surfaces. I have now two surfaces. Okay. One surface is, let's call it this surface S1, which is just this flat surface on this Amperian loop. And let there be another surface which is the same has the same boundary, but it is like a balloon like that. All right. So let me call that as surface S2. So they have the same boundary, and hence B dot dl should be the same, correct? Okay. So what is the I enclosed in this case, in these two cases? Let's look at that. So the total current passing through the this loop, of course, that is, or more precisely, the current the piercing through the surface S1 or S2 that has the loop as the common boundary. Okay, let's look at that. So for the surface S1, it is, of course, I enclosed is I, going like that. And but what was over the surface S2? I enclosed is 0, because no current is piercing. This is only the surface piercing through it. So I enclosed is 0. So that's a they have the same boundary. It should be mu enclosed, but no, this surface uh, has no current enclosed. And that's a big gap in the consistency of applying this to uh, to even this simple case of charging of a capacitor. Okay, so now the such conflict arises when charge is piling up somewhere. Okay, in this case, of course, the capacitor plates, the charge is piling up here, and for non-steady currents, the uh, the current enclosed by a loop is ill-defined. It depends on the surface you choose. Okay, you use. All right, not so, it's use. All right, so if I use this, then I enclose is 0. If I use this surface, I enclose is I. So Maxwell fixed this inconsistency, okay, by using theory, and that was 1861. Okay, so 1861 is typically considered as the year when Maxwell's equations, all those equations, became Maxwell's equations because of his fixing of this inconsistency in Ampere's law, and it has big consequences. Of course, the experimental confirmation came only from experiments of Hertz with electromagnetic waves much later. That's about in 1888, about 27 years later than first it was proposed. And we'll see why. Okay, so this was the, we can call the master stroke of Maxwell. Okay, says that just fixing the Ampere's law, all four laws become Maxwell's equations. So his magnum opus was published in 1865. It was called a dynamical theory of electromagnetic field. So recall the inconsistency due to Ampere's law for non-steady currents is was because that divergence of is not equal to 0 if the divergence of J is not 0. That is, if steady state J is not there. So that was the inconsistency you're talking about. So from continuity equation and Gauss's law, we can always write down that divergence of J is minus del rho by del T. Okay, and uh, that is, I can now rho, I can write down from the Gauss's law as epsilon naught divergence of E. All right, so and hence I can now take the del out and minus, okay, so epsilon del E by del T. All right, so divergence of epsilon del E del T, that is divergence. So now if I now bring this to this side, okay, then divergence of J, then this term, this plus term, okay, then it becomes 0. So here it was, even if it is non-steady current, this new quantity J plus epsilon del E by del T is equal to 0. So the crucial argument is through really is through the continuity equation. Okay, though Maxwell himself did not use this. He had another. This came up in his, but his main primary motive was something else, which we will not discuss because at that time this was around the ether, which we know it's not there. So whatever is it as it may be, it's now looks like if I, instead of just J, if I include this, that would fix it, right? So if I, instead of J, I say J, the current, plus this quantity, epsilon del E by del T. Okay. So in that case, of course, divergence and del dot, and that is equal to 0. Then it is, okay. And then we can say that the fatal inconsistency is now cured. Okay. If you admit that this also can be a part of the Ampere's law, and hence Ampere's law stands modified as del cross B mu naught J that was used to be there, and now just add this term. So J, and in addition mu naught, a new term which behaves like another current. Okay, uh, so this brings into certain aesthetic symmetry into the equations also. So symmetry of rate of change as source of fields. For example, we had uh, Faraday's law, that is, rate of change of B determines the electric field, the induced electric field, the electric field. Okay, so that was Faraday's law, and it's a changing magnetic field induces electric field. Okay, so in Ampere's law now, so that was, so this was only it was not change, but a steady current induces magnetic field. That was Ampere's law. Okay, so now if I replace J by J plus epsilon del E by del T, then of course this can be considered as Maxwell's contribution. He calls this term, the new term, as the displacement current. Okay, it's a misnomer. There is no current really there. It is just rate of change of um, electric field. So rate of change of magnetic field can give rise to electric field, and rate of change of electric field should give rise to a current-like term and hence to magnetic field. Okay, so this was called the displacement current. That's why I have put a subscript D here. So now this is the new term, and so a changing is now it's a changing electric field induces a magnetic field. Suppose J is 0. Okay, even then, so del cross B is also del E by del T is del cross B. Okay, and del B by del T makes uh, del cross E. So this is this symmetry, that rate of change of magnetic field can give rise to electric field, and rate of change of electric field can give rise to magnetic field. Why is it that this was had to wait for so long to be discovered in Ampere's law? Even finally we came to know only in 1888 that it is indeed true experimentally. You'll notice that this mu naught epsilon naught is a later, as we'll come to know, is 1 by c square, and hence for this term to be able to compete with any free current in the laboratory, okay, this delta E by delta T, the rate of change has to be very, very high. Okay. Suppose I was some E naught sine omega t, then del E by del T will give me rise to omega cos omega t. And if that omega is very high, okay, then probably when multiplied with this, could multiplied with epsilon naught, could compete with J. And hence the contribution in most practical terms in the laboratory was difficult to detect, okay, because there was not fast changing E, okay, or the actual current, displacement current, was very small until electromagnetic waves become possible, where omega is very high. In fact, J can be zero, and yet you can have both uh, magnetic field and electric field. Okay, just by the rate of change of the two quantities. We'll study that in great detail in the next to next chapter. How does that fix Ampere's law in case of charging capacitor? I had shown two views, one a charging capacitor as if in the lab, the other was the mathematical. The mathematically is of course fixed. Does it fix the charging capacitor physical scenario? Okay, we asked that question. So the electric field between the capacitors, uh, plates, okay, we can see is, let's say it's very close, is not drawn that way, such that we ignore the fringing field. Okay, in that case, I can write down the electric field between the two plates as sigma by epsilon naught, and that if there is a charge q on the plate at any time, then q by a. So E is that. I'm just assuming that the two plates are very, very close as compared um, to the size of the plates of the area. Okay. So let us apply it to an Amperean loop as we had done earlier. Okay. So similar. So if I say del E by del T, okay, then I'm just taking the magnitude at the moment, 1 by epsilon naught A dq by dt, but dq by dt is nothing but I. So del E by del T is I by epsilon naught A. Okay. Now let's look at the surface. Surface S1 and surface S2, which we had seen earlier while looking at the inconsistency. Okay. So now let's get back to the modified Ampere's law. That is, curl of B is mu naught J plus mu naught the displacement current epsilon naught del E by del T. So that will give rise to B dot dl. Okay. So mu naught I enclosed. This is will give rise to the our ordinary Ampere's law mu naught I enclosed plus mu naught epsilon integral of del E by del T over dA. All right. So that is the new integral form of Ampere's law with along with this term. We'll have many problems of this nature. So for the surface S1, E is 0, okay, because it's outside, okay, and hence the I enclosed contribution comes only from here, from the first term, mu naught I enclosed, all right, and this term has nothing to contribute because outside for this surface E is 0. And what about for the surface S2? Okay, the I enclosed is 0. There is no current really. There is no real current passing through. But this integral, okay, is now E is sigma by epsilon naught. Okay, and that is will be dq by dt. So this I by epsilon a. So this will be I by epsilon naught. Okay, so this quantity because dot dA. So a cancels. This is I by epsilon naught. All right, and so then mu naught, so in both cases, okay, in one case it is mu naught I, in the other case this epsilon naught cancels and also mu naught I. So it is absolutely consistent. So by this method, this is still valid, and by this method is also valid. The same answer we get by both. Okay, so this physical situation is also is consistent now once we admit that the extra term put by Maxwell into the Ampere's law. So finally, we have the full Maxwell's equations. We can call them Maxwell's equations. Okay, so we have a divergence of E rho by epsilon naught. let us write it down as many times as possible. Uh, Del cross E minus del B. So E, so Faraday's law, Coulomb's law, okay, and divergence of B is 0, of course, and the modified Ampere's law. So this is the full set of Maxwell's equations, okay, and for which we have been actually working pretty hard. So electric fields can be produced either by charges or by changing magnetic fields. This either charge or by changing magnetic fields. Okay, and what about the magnetic field can be produced either by current or by changing. Okay, this symmetry, okay, is in fact, if it is unsymmetrical at all, is because of there is a possible source term here and there is no source term here. Okay, so aesthetically people have been looking for some way of magnetic charge such that this can become completely symmetric, but so far uh, there is of course always an effort, but there has been as long as you don't see experimentally, there is no magnetic monopoles. Okay, uh, so if you focus on the source, then you can write down a little slightly differently, okay, just to show. So del dot E, of course, rho by epsilon naught, and you can bring this on the left side, then del cross E plus del B by del T is equal to 0, and then del, of course, divergence of B is 0, and if you bring this one on this side, then mu naught J, okay. So this is the source terms, physical source terms, apart from time dependence. So rho by epsilon naught, mu naught J, and these are of course 0 in these terms. Okay, so there is way of looking at it. So Maxwell's equation gives you how charges, static or dynamic, produce fields. Okay, that is what it does, and the and the Lorentz force tells you how fields affect charges. So charges can be static or moving, okay, and Maxwell's equations will tell you the fields, okay. And once you know the fields, then Lorentz force will tell you how these fields affect charges. The whole content of the theory is now ready, all right. In fact, this is so powerful that once you have learned this, okay, you have a different spectacles for the whole world, okay. The world looks different with this paradigm under your belt, all right. So these are not just equations. We have been working for more than 2 months to give meaning into these equations through phenomena. So one is, of course, a framework, a theoretical framework, and the other is the theoretical framework's relation to actual experiments and results outside. So I have been trying very hard to actually put this two together so that each the insights of the theoretical insight goes into the experiment, and the experimental insight is enriched by theory. Okay, so this is actually a logical point, a logical high point in our course, that we have been wanting you to look at all electromagnetic phenomena, okay, whether you have studied or not studied, to be encompassed by these classical set of equations, which is a large part of phenomena involving charges and moving charges, and which I described right in my first lecture, the kind of things that it encompasses, okay, both in time and space, and in the range of phenomena that it explains. So let's go to Maxwell's equations in matter. Okay, so uh, del dot is 0. Um, this is our general Maxwell's equations. We'll keep writing down every time, okay, till it becomes a part of your bloodstream. All right. So so this is the whole set now, okay. And this in matter, we can see that we can convert this in terms of the displacement vector d. We have found it useful to do it in terms of only free charges. Here it includes all charges, okay. This of course remains the same, okay. This also remains the same. Divergence of b is equal to 0, and instead of b, we could write it down in terms of H and D. So in Maxwell's equations, matter is easier to write down in terms of, easier to deal with in terms of D and H, because in between there are constitutive relationship, because D is epsilon E. And for linear materials, we have defined epsilon as this, okay, and H as B, and mu is, okay. So these are the constitutive relationships which takes to the Maxwell's equation to Maxwell's equations in matter. All right. How did I get that? Let me remind you a little bit. Okay. So the total charge density is of course rho free and rho bound, and we know the bound charge is minus divergence of the polarization P. All right. And so divergence of E, you could write down in terms of free minus divergence of plus, right? So we could write that down, and then we define D in terms of epsilon E plus P, displacement vector, and uh, this is then divergence of D is rho f. That's the first one. Okay, this we have done in a full chapter. Okay, now the total current density, the total current density J is equal to the free current, the bound current. I'm introducing another possible current which is called the polarization current, okay, which is not because of the del cross M, the bound current that we have seen. Okay, so I'm introducing the polarization can actually contribute another current del P by del T. All right. So and then this all currents must be included in the in matter. Okay. So mu naught, all three currents, JF, JB plus JP, and of course displacement current. All right. This of course you can write down in terms of del D by del T. So since Maxwell called D as a displacement vector, okay, this is called displacement current. In any case, Maxwell thought that as if there is something getting displaced, for actually he thought it's a current, okay, and named it as a current. So as if there is things something is, or in something in the medium is getting displaced, and that is why he called this as a displacement vector, and this current is the displacement current. Of course, it is not any physical current. Okay, so this, if we now replace H by B by mu naught minus M, then you can write down it in this form. All right. So these two are the ones which get modified through these relationships, and we have gotten the whole set of Maxwell's equations in matter. All right. Now, this is a curious new thing that I have not talked about so far. So let's talk about that. So let's call it JP, dP by dt, which is very different from JB. JB is del cross M. Okay, there is nothing to do with this is magnetization. Okay, but there is no in polarization. We'll look at the physical origin of this. So polarization current. What is the physical origin? Okay, I called it del P by del T. You can think of as there is a polarization P, and this is perpendicular surface. So P dot N will produce a minus sigma bound current and plus sigma bound current. And now, if there is a change in polarization, then this sigma bound and plus sigma bound will also change and increase. And that can be, that can be actual physical movement of the bound charges a little bit, right? And that will carry through to finally produce a bound current here. So it look like as if there is a flow of the bound charge from one phase to the other. Okay, so that is the boundary. There is no corresponding magnetic current like this. Okay, because there is actual movement of charges. So if I change as a function of time of course. Okay, if I P is changing, which means there is a polarization and it is changing, so that is now processed through such that there is a change in both sigma minus sigma B and plus sigma B. All right. So this is polarization current density. Okay. So polarization is P introduces plus b, sigma b and minus sigma b at the two ends. Okay, if p increases, then bound charges on each end also change accordingly if it increases or decreases, giving rise to a net current. Okay, there's not actual physical charge going from one end to another end, but there is apparently bound charge changing such that it shows up, the change shows up in the two plates, and that's like a current. Okay, so if I, so what is that current? So del sigma by del t, if this is the perpendicular area, then del p by del t dA perpendicular. All right, so I can generalize this to jp by del p by del t. Now, is this consistent with continuity equation? That one must change. If it is actually a current, then one must check whether it is consistent with continuity current, because continuity current seems has a pivotal role in making my Maxwell's equations consistent, right? So we must check that this indeed follows. So if I take divergence of Jp, then divergence of del P by del T, but that is I can take the divergence inside, then divergence of P, but divergence of P is minus, okay, sigma del sigma by del T. And so that is indeed a continuity equation. Divergence of Jp is giving rise to by minus del B, del sigma B by del T. All right. Yes, since bound charge is conserved. Okay. So now let's look at the last part, which is of course Maxwell's equations to be solved anytime in any particular situation requires boundary conditions. And we have done boundary conditions in electrostatics, in magnetostatics, and let's now lay down all the boundary conditions for Maxwell's equations, especially in a media. In media, there can be boundaries and interfaces, and we'll have to deal with it. So in the media, of course, I'm rewriting Maxwell's equations in matter. Okay, so that is my Maxwell's equation in matter, and that I'll how does then where do we get our boundary conditions from? From the integral form of these Maxwell's equations. Okay, and then we apply, you remember, little Gaussian pillboxes or little Amperian loops on the at the interface between two things. Okay, either vacuum and material or between two materials at that interface. And hence, let us write down the integral form of Maxwell's equations. Of course, that is if I integral over the surface, Gauss's law, then Q total Q free enclosed within the volume. So, and if I have E dot dl, then of course minus this. Okay, this is the same as the other one. B dot dA is of course 0, converting this into its integral form, and converting this into its integral form will give you d by dt d dot dA. So this is Maxwell's equations in differential form in matter, and this is Maxwell's equations in integral form in matter. So one can take especially these equations and then apply to our old technique of finding out the boundary condition. Okay. So the point is we always find out the boundary conditions from the integral form of Maxwell's equations. Um, uh, Okay, so let's just go through quickly boundary conditions again. So if the normal components to be figured out for B and D, okay, what do we use? We use a wafer thin Gaussian pillbox so that it takes, I think I have a figure, yeah, so that it's protruding slightly into the material 2 and material 1. Then of course D1 and D and B can be figured out. So D dot dA is Q free enclosed. I'm just giving an example, but you can do it for any of those equations. And so D1 perpendicular and D2 perpendicular must be if there is only if there is a free charge. Okay, and then B dot dA is equal to 0, which means the B1 perpendicular and B2 perpendicular must be equal. Okay, so that must be equal to 0. For the parallel components, of course, you take a small, just as an example for B, you can take an Amperian loop which straddles the surface, straddling the surface, and then E dot dl, you can minus D dot B dot A, and you can obtain that E1 is parallel to E2, which is true. Okay, and but for H, if there is a free current KF, then it will have an effect, and so that will be H1 parallel H2 parallel KF cross M. Okay, this is something similar that we have already discussed, the same techniques, but for sake of completeness, I want to put it together. So D perpendicular, B perpendicular, E1 parallel, H1 parallel. Okay, we have the complete set of boundary conditions that we can apply. Okay, so I can even summarize further general boundary conditions for electrodynamics. Okay, so D1 and D2, if there is a free charge at the interface, otherwise B1 and B1 normal and B2 normal are equal. E1 parallel is always equal. H1 parallel, of course, depends if there is a free current at the interface. So these are the general boundary conditions for electrodynamics. But in case of linear media, one can simplify. So instead of D1, you can write down epsilon 1 E1, because we know I can write down the linear relationship. And so it just, okay. Similarly, if it is linear media and magnetic material, then B1 parallel by mu1 minus mu2 is KF cross M. All right. And if there is no sigma F and KF, obvious, okay, there is both, these both are zero. The normal components are zero and parallel components are also zero. So no free charge, no free current. Then I can write down this special case. This will be very useful to us in dealing with the reflection and refraction of waves at the interface between two media, as we do going to a chapter in the next chapter, where we deal with electromagnetic waves. So with that, I've come to the conclusion of the Maxwell's equations. We'll of course have a lot more to discuss about them in terms of energy and the potential formulation. But logically, we have everything on our, all the possible tools of electromagnetic phenomena spread out in front of us to be able to understand or deal with any phenomena over a huge range. All right. So we will start taking it forward now, applications, okay, of these Maxwell's equations, and see the consequences of Maxwell's change of the Ampere's law, and putting this nice theory, its effect on many applications. Okay, so that we'll see soon. All right. Okay, so that's so this is for this week.